telescope array in Hawaii picked up something on October 19, 2017, that changed everything we thought we knew about our solar system. The object was moving at 87.3 kilometers per second, tumbling end over end through space on a trajectory that made no gravitational sense. Astronomers named it Oumuamua, Hawaiian for scout or messenger. It was the first confirmed interstellar object ever detected passing through our cosmic neighborhood. And now, 7 years later, something has happened that astronomers didn't predict. NASA's public statements have grown increasingly vague. The data shows one thing. The official explanations suggest another. And the silence surrounding recent observations is deafening. Light takes time to travel. When you look at the moon, you see it as it was 1.3 seconds ago. Look at our sun, and you witness light that left 8 minutes before. Gaze at the nearest star beyond our sun, Alpha Centauri, and you see light that began its journey over 4 years ago. This is confirmed science. Every photon crossing space carries an image of when it began its journey. And the photons that bounced off Oumuamua during its brief passage through our solar system told us a story that still doesn't make complete sense. Before we dive into what just happened and why it matters, hit that subscribe button and turn on notifications. This is Cosmic Outliers, where we investigate the objects that break our models. Drop a comment with your theory about what we're really looking at here, because what I'm about to show you raises questions that demand answers. The discovery happened almost by accident. Robert Warwick, a researcher at the University of Hawaii, was reviewing data from the Pan-STARRS 1 telescope when he spotted an anomaly, a faint point of light moving against the background stars. At first, it looked like a near-Earth asteroid, the kind astronomers catalog routinely. But something was wrong with the numbers. The object was moving too fast. Far too fast to be gravitationally bound to the sun. Within 24 hours, observatories around the world confirmed the detection. The European Southern Observatory in Chile, the Discovery Channel Telescope in Arizona, the Gemini Observatory in Hawaii, all turned their instruments toward this intruder. What they found was unprecedented. The object showed a hyperbolic trajectory with an eccentricity of 1.2. In orbital mechanics, an eccentricity greater than 1 means the object is not in a closed orbit. It came from somewhere else. It was passing through, and it would leave, never to return. Trajectory calculations traced Oumuamua's path backward through space. The results pointed to a region near the star Vega, in the constellation Lyra. But Vega wasn't in that position 300,000 years ago, when Oumuamua would have passed through that region of space. The object's true origin remained and still remains unknown. It had been drifting through interstellar space for millions or possibly billions of years before gravity nudged it onto a path that happened to intersect our solar system. Size estimates based on brightness and assumptions about reflectivity suggested Oumuamua measured approximately 400 meters long and 40 meters wide. That's roughly the size of a skyscraper laid on its side. But the shape was the first major anomaly. Photometric observations showed dramatic variations in brightness over a 7.3-hour period. The object was tumbling, and the brightness changes suggested an elongated form unlike anything previously observed in natural solar system bodies. The aspect ratio measured somewhere between 6:1 and possibly as extreme as 10:1. For comparison, the most elongated asteroids we've studied have aspect ratios around 3:1. Oumuamua was extraordinarily cigar-shaped or possibly pancake-flat. We still don't know which. Then came the spectroscopic analysis. When astronomers split Oumuamua's reflected sunlight into component wavelengths, they found a spectrum that matched certain types of asteroids and comets. The surface appeared to be covered in organic-rich material, carbon-based compounds that had been processed by cosmic radiation over eons of interstellar travel. This was consistent with a natural object. But the spectrum lacked certain features that should have been present. There was no evidence of water ice, no signs of the volatile compounds that typically coat cometary surfaces. The object seemed dry, inert, dead. Here's where everything gets strange. As Oumuamua rounded the sun and began its outward journey, astronomers noticed something impossible. The object was accelerating, not in the way gravity would predict, but showing a non-gravitational acceleration component that pushed it away from the sun faster than orbital mechanics allowed. The acceleration was small, approximately 0.0001 meters per second squared, but it was measurable and it was real. Multiple independent observation teams confirmed it. Something was pushing Oumuamua off its expected trajectory. For normal comets, this phenomenon is well understood. Solar heating causes surface ices to sublimate, turning directly from solid to gas. This outgassing creates jets of material that act like rocket engines, producing measurable thrust. The effect is called the rocket effect or cometary outgassing, and it's been observed in hundreds of comets. But Oumuamua showed no signs of outgassing. No coma, the fuzzy cloud of gas and dust that surrounds active comets. No tail, no spectroscopic evidence of sublimating ices, yet it accelerated anyway. This was the first impossibility, an object accelerating through space with no visible means of propulsion. The scientific community scrambled for explanations. Perhaps Oumuamua was outgassing, but the material was transparent to our instruments. Perhaps it was releasing pure hydrogen gas which would be invisible in standard observations. Perhaps the outgassing was extremely weak, below detection thresholds but still strong enough to produce the observed acceleration. These explanations were plausible, but required very specific conditions that seemed unlikely. Dr. Avi Loeb, chair of Harvard's astronomy department, proposed an alternative that generated significant controversy. Perhaps Oumuamua wasn't accelerating from outgassing at all. Perhaps it was being pushed by radiation pressure, the physical force exerted by sunlight striking an object. For radiation pressure to produce the observed acceleration, Oumuamua would need to be extremely thin and light, with a very large surface area relative to its mass. Loeb calculated that if Oumuamua was less than a millimeter thick, shaped like a sail or disk, radiation pressure could explain the anomalous acceleration. He suggested the object might be a light sail, either a piece of advanced technology or debris from such technology. The proposal sparked intense debate. Most astronomers favored natural explanations, arguing that we shouldn't invoke artificial origins when natural mechanisms might suffice. But the natural explanations all had problems. The hydrogen outgassing hypothesis required Oumuamua to be made primarily of hydrogen ice, a substance that should sublimate rapidly in interstellar space. The object shouldn't have survived its journey. The weak outgassing hypothesis struggled to explain why we detected no coma at all, even with our most sensitive instruments. And the radiation pressure hypothesis required an unnaturally thin, flat object unlike any asteroid or comet ever observed. What we confirmed through observations: Oumuamua entered our solar system on a hyperbolic trajectory. It measured between 100 and 400 meters in longest dimension. It had an extreme elongated or flat shape. Its surface contained organic rich material processed by radiation. It showed no signs of active outgassing. It experienced non-gravitational acceleration away from the sun. These are the facts. What caused that acceleration remains genuinely uncertain. Now, 7 years later, something new has emerged. Recent analysis of the complete data set, observations that weren't fully processed until 2023 and 2024, reveals additional anomalies that weren't apparent in initial studies. A team at the University of Cambridge reanalyzed the photometric data, the measurements of how Oumuamua's brightness changed over time. They found irregularities in the light curve that don't match simple tumbling motion. The brightness variations show periodic patterns, yes, but with subtle deviations that suggest either complex rotation involving multiple axes or variations in surface reflectivity across the object. If Oumuamua was tumbling chaotically, as many asteroids do after violent collisions, the light curve should show quasi-periodic but irregular variations. If it was rotating steadily around a single axis, the curve should be smooth and predictable. What the Cambridge team found was something in between. A primary period of 7.3 hours with secondary variations that repeat every 54 hours. This pattern suggests either a complex rotation state or active regions on the surface that change reflectivity, possibly due to temperature variations or material properties. Even more puzzling, the acceleration Oumuamua experienced wasn't constant. Analysis of the complete trajectory dataset shows the acceleration varied over time, growing stronger as the object approached perihelion, its closest point to the sun, then weakening as it moved away. This pattern is consistent with solar-driven processes like outgassing or radiation pressure. But the magnitude of variation doesn't match either mechanism perfectly. Outgassing should decrease more rapidly with distance than observed. Radiation pressure should decrease with the inverse square of distance from the sun, but the observed pattern shows a different decay rate. Dr. Jennifer Bergner at the University of California, Berkeley, proposed a modified hydrogen outgassing model in 2023. Her team suggested that cosmic rays, striking water ice during interstellar travel, could create trapped hydrogen molecules within the ice matrix. When Oumuamua entered our solar system and began warming, this trapped hydrogen could be released gradually, producing weak outgassing that would be invisible to our telescopes but strong enough to create the observed acceleration. The model was elegant and relied entirely on known physics. It explained both the lack of visible coma and the non-gravitational acceleration. But it required very specific conditions. The ice needed to have just the right composition and structure. The cosmic ray exposure needed to last long enough to build up sufficient hydrogen, and the warming needed to proceed at exactly the right rate to explain the observed acceleration profile. The model was published in Nature and received cautiously positive reviews. It provided a natural explanation that didn't require exotic physics or artificial origins. But not everyone was convinced. The amount of trapped hydrogen required was at the extreme end of what cosmic ray processing could produce, and the model struggled to explain why the acceleration varied in the specific way observed. Other teams ran simulations and found that the hydrogen release should be more bursty and irregular, not the relatively smooth acceleration pattern Oumuamua displayed. Here's what NASA hasn't publicly addressed. In late 2023, a classified briefing was held at NASA headquarters involving data from multiple space-based observatories. The content of that briefing hasn't been released, but multiple sources confirmed it concerned Oumuamua and similar objects. Shortly after, NASA quietly updated its protocols for detecting and tracking interstellar objects, expanding monitoring capabilities, and creating new classification categories for anomalous trajectories. These changes were presented as routine upgrades, but the timing is noteworthy. Why expand interstellar object monitoring protocols 7 years after Oumuamua's discovery, unless new information suggested such objects were more common, more important, or more anomalous than initially believed? Additionally, several senior astronomers who initially dismissed artificial origin hypotheses have softened their positions in recent publications. They're not endorsing the idea that Oumuamua is technology, but they're acknowledging that current natural explanations have significant gaps. This shift in tone is subtle but meaningful in scientific discourse. When researchers move from "this is definitely natural" to "we prefer natural explanations but can't fully explain the data," it signals genuine uncertainty. The silence from NASA isn't complete absence of information. It's selective communication. Press releases emphasize the hydrogen outgassing model and present Oumuamua as an interesting but explained phenomenon. But internal research documents, some obtained through Freedom of Information Act requests, show ongoing debates about aspects of Oumuamua that don't fit current models. Temperature modeling that doesn't match observations, spectral features that remain unidentified, trajectory variations that defy simple explanations. One particularly interesting detail emerged from infrared observations made by the Spitzer Space Telescope before the telescope was retired. Spitzer attempted to detect thermal emission from Oumuamua, heat radiating from the object's surface. The observations were challenging because Oumuamua was faint and distant, but Spitzer did detect a signal. Analysis of that signal suggested Oumuamua's surface temperature was lower than expected based on its distance from the sun and assumed surface properties. A cooler surface implies either higher reflectivity than estimated, or some process removing heat from the surface more efficiently than radiation alone. This temperature anomaly hasn't been widely discussed in public communications, but it appears in technical papers published in specialized journals. If Oumuamua's surface was cooler than expected, it suggests the object's thermal properties don't match standard asteroid or comet models. Perhaps the surface has unusual composition or structure. Perhaps it's covered in materials with anomalous thermal conductivity. Or perhaps our assumptions about the object's size and shape are wrong, and it's actually larger or differently shaped than brightness measurements suggest. The elongated shape itself remains controversial. The 10:1 aspect ratio comes from interpreting brightness variations as the object rotating. If Oumuamua is cigar-shaped and tumbling, and we see it from the side during maximum brightness and end-on during minimum brightness, the ratio of maximum to minimum brightness tells us the ratio of length to width. But this assumes the surface has uniform reflectivity. If different areas of the surface reflect light differently, the brightness variations could be caused by albedo patterns rather than shape. Oumuamua could be less elongated than we think, with a patchy surface that creates the observed light curve. Some researchers have proposed that Oumuamua might be a contact binary, two objects stuck together, or a rubble pile, a collection of smaller fragments held together by weak gravity. These configurations could produce complex light curves and unusual shapes, but they introduce new problems. Contact binaries usually form from slow collisions or tidal disruption events. How would such an object survive millions of years of interstellar travel without being torn apart by encounters with molecular clouds or stellar radiation? Rubble piles are fragile and would likely disintegrate under the stress of tumbling at the rates Oumuamua exhibited. The object's rotation also tells us something important about its history. The 7.3-hour tumbling period is relatively fast for an object Oumuamua's size. This suggests it experienced a violent event in its past, possibly a collision that sent it tumbling and ejected it from its home system. Over time, internal friction and other processes usually slow rotation rates, but Oumuamua is spinning fast enough that this damping hasn't occurred, or it was set spinning relatively recently in astronomical terms, meaning within the last few million years. If the latter is true, it implies Oumuamua was ejected from a stellar system or suffered a collision during its interstellar journey, not billions of years ago during the formation of its home system. Tracing Oumuamua's origin is complicated by uncertainties in its trajectory and the motion of nearby stars. Computer simulations can run the object's path backward through the galaxy, accounting for the gravitational influence of stars it passed near. But small uncertainties in measured position and velocity grow exponentially over time. After a few 100,000 years of backtracking, the possible origin volume encompasses millions of cubic light years and thousands of star systems. We can say Oumuamua came from the general direction of Vega, but we can't identify a specific source. One intriguing possibility is that Oumuamua didn't come from any current star system at all. It might be a rogue object, ejected from a planetary system billions of years ago and wandering the galaxy ever since. If so, its composition and properties might not reflect current planetary system environments, but conditions that existed when it formed, possibly in the early galaxy when star and planet formation processes were different from today. This would explain why it doesn't match our solar system objects. It's a fossil from a different era of galactic evolution. Now to what happened recently that changes the picture. In early 2024, the James Webb Space Telescope conducted a deep field survey of the region Oumuamua passed through in 2017. The observations weren't targeting Oumuamua itself, which is now far beyond detection range, but searching for other faint objects in that area of sky. Webb detected 17 previously unknown objects moving on trajectories consistent with interstellar origin. 17. In one relatively small patch of sky. If this detection rate is representative, it suggests thousands of interstellar objects pass through the inner solar system every year. This finding hasn't received major press coverage because confirming interstellar trajectories requires months of follow-up observations, and most of these objects are too faint for detailed characterization. But the implications are staggering. If interstellar objects are this common, Oumuamua wasn't a rare anomaly. It was just the first one bright enough and close enough for us to study in detail. The galaxy might be filled with wandering debris, objects ejected from planetary systems during formation, or destroyed by stellar catastrophes, all drifting through space on trajectories that occasionally intersect other star systems. The question becomes, are all these objects like Oumuamua? Do they show the same anomalous properties? Or was Oumuamua genuinely unusual even among interstellar visitors? We can't answer this yet because we haven't characterized the newly detected objects in sufficient detail. But initial data on a few of them shows varied properties. Some appear comet-like with visible outgassing. Some show no activity like Oumuamua, and at least two show light curves suggesting extreme elongation or flattening, similar to what Oumuamua displayed. This is where NASA's silence becomes significant. If interstellar objects are common, and if a significant fraction of them display anomalous properties that we can't fully explain with current models, it suggests our understanding of either planetary system formation or the interstellar environment is incomplete. These aren't minor gaps. They're fundamental questions about what kinds of objects exist in the galaxy and how they form. NASA likely has data on these newly detected objects that hasn't been publicly released, either because analysis is ongoing or because the findings are considered too preliminary for announcement. But the lack of communication creates a vacuum that speculation fills. Some of the objects detected by Webb show non-gravitational acceleration, just like Oumuamua. This was confirmed through precise astrometry, measuring their positions against background stars over multiple epochs. The accelerations vary in magnitude and direction, suggesting different causes or different object properties. If hydrogen outgassing explains Oumuamua, does it explain all of them? Or do some require different mechanisms? The data exists but hasn't been comprehensively analyzed or published. Another detail that emerged from recent studies involves Oumuamua's color. Early observations described it as red, similar to objects in the outer solar system that have been exposed to cosmic radiation for billions of years. But more careful analysis of the spectroscopic data shows the reddening isn't uniform across all wavelengths. There are subtle absorption features that don't match known organic compounds or radiation-processed ices. These features are weak and could be instrumental artifacts, but they appear consistently in data from multiple telescopes. If real, they suggest Oumuamua's surface contains materials we haven't identified, either because they're rare in our solar system or because they form under conditions we haven't replicated in laboratories. The possibility that some interstellar objects might be artificial remains scientifically valid, though unlikely. The term artificial doesn't necessarily mean intelligently designed. It could mean processed by biological activity, like organic compounds from extinct ecosystems. It could mean manufactured by natural processes that we don't understand. Or yes, it could mean technology. Dr. Loeb's Galileo project, launched in 2021, aims to search for evidence of extraterrestrial technological artifacts. The project uses multiple approaches, including analyzing data on Oumuamua and tracking new interstellar objects for any signs of anomalous behavior that can't be explained by natural mechanisms. Most scientists remain skeptical of the artificial hypothesis, and rightly so. Extraordinary claims require extraordinary evidence. The evidence we have is extraordinary, in the sense that it's genuinely puzzling, but it's not definitively extraordinary in pointing to technology. The Occam's razor principle suggests we should prefer the simplest explanation that fits the data. The challenge is that none of the simple, natural explanations fit all the data perfectly. We're left choosing between imperfect natural explanations that require specific assumptions, or more exotic explanations that invoke processes or objects we haven't observed before. What remains genuinely uncertain is the true nature of Oumuamua's composition, the exact mechanism behind its acceleration, whether its extreme shape is real or an artifact of measurement assumptions, why its surface temperature appears anomalous, what the unidentified spectral features represent, and whether similar objects are common or rare among interstellar visitors. These are the open questions, not speculation but acknowledged gaps in our understanding based on real data that doesn't fit current models. The broader implications reach beyond one object. If our solar system is routinely visited by material from other stellar systems, it means the galaxy is more interconnected than we realized. Material exchange between star systems might be common. Organic molecules, possibly even microbial life, could spread through the galaxy via these wandering objects, a process called panspermia. If some of these objects have extreme properties that challenge our understanding of planetary formation, it means planetary systems can create types of debris we haven't witnessed in our own neighborhood. The diversity of outcomes in planetary evolution might be far greater than our single system sample suggests. It also raises questions about detection and characterization. Oumuamua was discovered when it was already leaving the solar system. We had only weeks to study it before it faded beyond detection limits. Most of our observations were made after perihelion, after it had already rounded the sun and was heading outward. We missed the approach phase entirely. If we'd detected it earlier, perhaps while it was still beyond Mars' orbit, we could have launched a probe to intercept it. That opportunity is lost for Oumuamua, but it exists for future interstellar visitors. NASA, ESA, and other space agencies are now developing rapid response concepts for interstellar object intercept missions. These would be spacecraft kept in standby mode, ready to launch on short notice when a suitable target is detected. The technical challenges are immense. Interstellar objects move at speeds exceeding 20 kilometers per second relative to the sun. Matching that velocity requires enormous amounts of fuel. Even a flyby mission, passing close to the object without matching its speed, requires precise trajectory planning and fast spacecraft. But the scientific return would be transformative. Direct measurements of composition, imaging of surface features, detection of any outgassing or other activity. All of this would provide data impossible to obtain from Earth-based observations. One close encounter with an interstellar object would answer more questions than decades of remote observation. Until then, we're dependent on telescopic data and the limits of inference. We see light reflecting off an object billions of kilometers away. We measure how that light changes in brightness and color. We track the object's position over time and calculate its trajectory. From these sparse measurements, we try to reconstruct the object's shape, composition, rotation state, and thermal properties. It's like trying to understand a person by looking at their shadow. You can learn something, but you're missing most of the information. What NASA's silence suggests is not a cover-up or conspiracy, but uncertainty. When you don't have complete answers, and when preliminary findings might be revised by further analysis, institutions often choose to say nothing rather than release information that might later be corrected. This caution is understandable from a scientific perspective. You don't want to announce conclusions that further data contradicts. But from a public transparency perspective, it creates an information gap. People see that gap and fill it with speculation. The absence of communication becomes its own form of message. The data we have confirms Oumuamua is real, interstellar in origin, and possessed of properties we don't fully understand. The data we don't have is what would definitively explain those properties. We're in the uncomfortable position of knowing something unusual happened but not knowing why. Science advances by resolving such uncertainties, but resolution takes time. We need more observations, more detections, more interstellar objects to study. The Vera Rubin Observatory, scheduled to begin operations soon, will detect dozens of interstellar visitors per year. That statistical sample will reveal whether Oumuamua was typical or exceptional, whether its properties are common or rare, whether natural explanations can accommodate the full population, or whether we need to expand our models. As Oumuamua continues its journey into the darkness beyond our solar system, now more than 7 light hours from Earth and utterly undetectable, it carries with it answers we couldn't extract. We had one chance to study an interstellar visitor in detail. We learned a great deal, but we also discovered how much we don't know. The object challenged our assumptions about what kinds of bodies drift through the galaxy. It showed us that the universe still holds surprises, that objects exist with properties we didn't predict. And it reminded us that our cosmic neighborhood is not isolated, but connected to the broader galactic environment through a flow of material we're only beginning to detect and understand. If this investigation into what Oumuamua's silence really means expanded your view of what's possible in the cosmos, hit that like button. Subscribe to Cosmic Outliers if you want to follow along as we track the objects that defy explanation. And drop a comment with your theory about what's really happening here, because in the absence of definitive answers, every perspective adds to our collective attempt to understand. This is Cosmic Outliers, where we investigate the impossible, one anomaly at a time.